Hello, my name is Fred. Welcome to Awesome State Management for React. Why awesome? Well, what I'd like to show you today is not a library. It's just a simple pattern. And because it's not a library, you don't have to wait for me to release features or bug fixes. You don't have to worry about compatibility issues. And most importantly, you are not tying your code to a specific library and API. So I mentioned React, but if you like to use another virtual DOM library, this pattern works easily with Preact, SnapDOM, Inferno, Mithril, the list goes on. Now, when React came along and made the virtual DOM more well known, we realized that the virtual DOM is actually very nice. It lets you write functions of the model to produce your view. This makes views easier to write and assemble, compose, test, and debug. So once you get used to this idea, you're thinking, I love React. And then, oh man, I hate React. How do I manage state? Do I use state, component state, props? Do I use Flux? What is Flux? Well, there are some very good solutions out there. But my problem with Redux, for example, is that there's a lot of boilerplate involved with action constants and every reducer being called for every action, so you need an if or a switch case, and thunks, sagas. It just seems like a lot has to pile on. With MobX and Cerebral, these are nice solutions as well, but in those cases, you really have to commit to tying your state management code to their API. Cycle is a different solution altogether, but I mention it because it does have some interesting ideas. Again, you're going to be tying up your model in several stream operators. So I just want to make it clear that I am not knocking these solutions because there's are very good things to learn from them and they are excellent. But today I'd like you to open your mind and consider a different approach. It's called Meiosis, and there you have the website. Now please know that all the slides from this presentation are available there as well as all the code examples. So if things go by a little too quickly, please stay with me and know that you can go back and look at all the code and all the examples in more detail. So the idea of the meiosis pattern is this. We start with a model or application state, and this is your single source of truth. Then you write your views as functions of the model. Then you need a way to update your model. And when you do that, we want the view to be automatically re-rendered. So let's look at a simple counterexample. Our initial model is a simple JavaScript object with a counter value of 0. This is our model and single source of truth. Then our view is a function of the model. Here I am just displaying the counter. Note that I am using JSX, but of course you can also use a solution such as JSNoX combined with React, or of course if you like another virtual DOM library, you use your preferred API. Now that we have a model and a view, what we do is we create actions that the view will be able to call. Here we have an increment action that will increment the counter. Notice that to create the actions, we're passing in an update. This is a function that we can call, and when we do that, we will pass in a function that will update the model. This function gets the latest model, makes the changes, and returns a new model with the updated values. After we call update, we want the view to be automatically re-rendered. Now that we have created actions, they are convenient for the view to call. So here we are passing the actions to create the view as a function of the model. We're displaying the counter, and then we have a button to increment. And we can easily associate the onClick handler to the increment action. That will update the model to increment the counter, and the view will be re-rendered to show the new value. So the question is, what is update? How do we make that update automatically re-render the view? Well, there are different ways to implement the meiosis pattern. What I like to do is use a minimal stream library. And when I say minimal, I only need map and scan. And as you'll see, I only need them in one place. Now, if you really don't want to use a stream library, you can also write your own minimal implementation of the pattern, and it's really not difficult. So what I'm using is a simple stream library called Flyd. If you're not familiar with streams, just think of them as arrays of values that are not just a fixed number of values, but values that just keep coming over time. To create a stream with Flyd, we just have to call Flyd.stream. Then, if we want to do something every time a new value comes in, we call map. If we pass in a function, every time a new value comes in, whatever we return from that function will be the new value on the resulting stream. So here we have a second stream that will be just all the values from the first stream multiplied by 10. We can also use map to perform side effects. So here I'm calling map on the second stream, and I'm logging the values to the console. With Flyd, to push a value onto a stream, you call the stream as a regular function and you pass in the value. So here I am passing 5 and 10 onto the first stream. That means the second stream values will be 50 and 100, and because I'm calling console log on the second map, I will see those values on the output. The other operator that we need is scan. Now, scan is a lot like reduce. What scan does is it starts with an initial value, it looks at the values coming in from the source stream, and it takes a function of two parameters. So every time a new value comes in the source stream, the two-parameter function will be called with the latest value, starting with the initial value, the value that just came in the source stream, and whatever we return from that two-parameter function will be the next value on the resulting stream. So in this example, my two-parameter function is addition. The initial value is 0. So that's the initial value in our resulting stream. Then, when we push 5 onto the source stream, the addition will be called on 0 and 5, and the result will be 5. But when 13 comes in, the latest value is 5 now, so 5 plus 13 will result in 18. Then when we push 24, 24 plus 18 is 42. And 42, of course, is the answer to the meaning of life and everything in the universe. We are now ready to implement the meiosis pattern. So we start with our initial model, which is our counter. Update is a stream. Now remember that we'll be calling it with functions to update the model. So that's a perfect candidate for scan. The initial value will be the initial model. The source stream is update. And our two-parameter function will get the model and then a function to update the model. So to get the next value, all we have to do is call that function on the model. And that will give us a stream of models. Finally, every time a new model comes in, we want to re-render the view. So we'll create our view, passing in the actions that we create, passing in the update stream, and then we'll call map on the stream of models. For every model, we'll re-render the view by calling view model, and we'll use React DOM to render the view into the element of the page. So every time update gets called, a new value comes in the stream, a new model gets produced, and the view is re-rendered. Now I mentioned that it's very easy to use a different DOM library. All we're doing is calling React DOM.render. So if you're using Inferno, you would call Inferno.render, or Preact.render, or Mithril, which is M.render. And at the bottom, you have the solution for SnapDOM and PicoDOM. So any virtual DOM library is just one line to change. Now let's look at model updates. There are different ways that you can update the model. Because the pattern is that you are passing in functions to update the model, you are free to decide how you're going to do this. It can be very simple, such as here we're just using plain mutation. There's nothing wrong with using mutation. If you like to use Lodash, you can use that and use its functions to update the model. You can use the Lodash FP functional programming version, which can yield even more concise code. Ramda is another nice utility library. And you can also use immutable.js, for example, even though it has a different API, because it's got, instead of plain objects, it actually has immutable objects with methods on them to produce new values. The point is that because you're passing in functions, you're free to do that, and the pattern will work because it will just call the functions that you're passing through. All right, let's talk about components. Components are somewhat of an overused term, and they can mean complex things in certain frameworks. In Meiosis, there's nothing magical about components. They're just plain objects with functions, and you decide the structure. So there is no hidden behavior. You're in complete control. Here is an example of a component. This is a temperature component, which will have a date that we can enter, a value that we can increase and decrease, and units which we can change between Celsius and Fahrenheit. So we have a function here to create our temperature component. We're passing in update, which is the same update stream that we had, and we'll be calling this as a function to pass in functions that update our model. Besides the model function that we are returning to create the initial model of our temperature component, we have the view, which we create as we did before. Here is a visualization of the example. As you can see, you can increase and decrease the temperature, change in units, and enter the date. So here we are creating our actions. We have an action to edit the date, which will just set the date on the model from the value in the text field. Then we have a function to increase or decrease the value of the temperature. Now we're passing in amount by which to increase. So we can use this to decrease as well, because that's just an increase of -1. Finally, we have a function, an action to change the units between Celsius and Fahrenheit, and that's just simple math. You can see here that there's nothing special going on in this code. It's just regular functions. Finally, we have the view, to which we pass in the actions and return a function of the model. We're rendering the view with the text field, which has the value from the model, and the onChange, which we'll call edit date. We're displaying the value of the temperature with the units. We have buttons to increase and decrease the temperature, and finally the button to change the units. So as you can see, everything is all neatly organized. The implementation of the meiosis pattern is the same as we had before. We have our update, which is our stream of functions to update the model. We're creating our temperature component by passing in update. The initial model now is the model returned by our temperature component by calling model. Our apply update and scan have not changed. And when we render the view, we're just calling temperature.view to call the component's view function. Before looking at more components, I'd like to show you the Meiosis tracer. This is a time travel development tool. If you've used time travel type tools before, it's nice to see that I'm not asking you to abandon those tools if you're trying to experiment with Meiosis. You can install the tracer in Chrome DevTools, and it will appear in a tab in the Chrome DevTools. You will be able to see a sequence of models as you interact with your view. And then you can time travel simply by going back in time and seeing all the snapshots of the model. You can even type directly in the text area, and you will see their changes reflecting in the view. Now, we have written our views as function of the model, so why not? We have a model and we have the resulting view. If you're not using Chrome or you do not want to install the extension for any reason, you can still use the tracer by adding it directly to your page, and it works the same way. Just to give you an idea that it's easy to use the tracer, all you have to do is install Meiosis as a development-only dependency, and then you install the extension. And to activate the tracer, you just call trace. You pass in your update stream and then an array of data streams that you'd like to observe. In our case, it's our stream of models. To use the tracer directly in your page, just add an element and a way of finding it. For example, you can give it an ID of tracer. Then, after calling trace, you call Meiosis tracer. You pass in a selector that matches your element, and that's where it will render the tracer for you. You can see that it's very easy to use a tracer both in Chrome DevTools and directly on the page. Let's talk now about more components. Let's say we want to reuse our temperature component twice on the same page, one for the air temperature and one for the water temperature. We really like to reuse our temperature component as is without changing it so that it can manage its own model. But we still want a single top-level model as our source of truth. How can we achieve this? Here we have our app that will contain our two instances of our temperature component. So we're creating an air and a water temperature component. But instead of passing update directly, we're going to nest it with a path to say which path we want it to be in the top level model. So here we have air and water path. Then the initial model of our app is air and water with the initial models of our two temperature components. Finally, we pass those components onto the view so that they can render them. So how do we nest the update? Well, because we're using plain functions, it's actually very easy to do. Remember that we're passing in a function to update the model from our components. So what we can do is wrap that, take the incoming model update, then we turn around and call the real update. We pass in a new function of the model, and then we update the model at that path. And we call that model update function, and we also pass in the model at that path. So for example, we'll update model.air or model.water. So our temperature component doesn't need to change and doesn't need to know that it's actually being nested. It just continues to work as it did before. And we're just intercepting the update to put it in the top level model. The view is simple because we just have to render the components where we want. And again, to nest the components, we just pass in model.air or model.water to those temperature components. As you can see here, now we have two instances of our temperature component. They're both independent of one of another, And we still have our top level model as our single source of truth. As you can see in our tracer, we have the air and the water properties, each with the models from our temperature components. Now that works, but you probably noticed that there's a lot of path repetition going on. And all that repetition will make our code more tedious to write and more error prone. If you look carefully here, there's actually two mistakes. In our model, the water is using the air components model instead of water because I copy pasted and forgot to make the change. And in the view, I forgot to pass model.water to the water component. So of course that will not work. We can eliminate all this path repetition. We can write a create components helper function that will take an update and a structure of our components. The air and water are the paths where we want to nest the components, and we just pass the function to create the component. And what create components does is call nest for us with the corresponding path. It will also wrap the view function to pass in the nested path to the view so that we can just pass in the model directly and not worry about it. We can also write a combine components helper function. We pass in our components and the property of the component that we want to call, which is model, and that helper function will call those functions on all the components and put them back in the same path. And that makes it easy for us to create the initial model. Finally, when we render the view, as you can see, we just pass in model to every component view function. So we've eliminated the path repetition because we just specify it in one place and then render the components in the view. I won't be going into details of the implementation of create components and combine components, but it's really not that difficult, and please have a look at the example code to see how they work. Or if you're feeling adventurous, why not try to first write them yourself? Because it's really not difficult. We're still dealing with plain objects and functions. Computed properties. These are properties that are a result of some kind of calculation on other properties of the model. We do not want to burden the view with those calculations, but we just want to make those values available for the view to display. We want to make sure that those computed properties are always up to date when the other properties of the model change. Well, this is very easy to do. Here's an example of a simple computed property. What we have here is a computed function which will take the model and add a comment on it. If the temperature is less than 10 degrees Celsius, we'll say cold. If the temperature is more than 40 degrees Celsius, we'll say hot. And in between, the comment will be blank. If the temperature was in Fahrenheit, we'll temporarily convert it to Celsius before deciding on the comment. To use this computed function, all we have to do is, instead of returning the view directly, we'll wrap it and take the incoming model. Then we'll call computed, passing in the model so that we get the computed properties, and then we'll pass the result of that to the view. If you like functional programming, you recognize this as function composition. So for example, here we could have used, say, ram_does_compose utility and passed in view and computed as the two functions through which the model will be passing, and we will get the same result. As you can see here, now if we decrease the temperature below 10 degrees Celsius, we get cold, and if we go above 40 degrees, we get hot, and again, both components are independent of each other. For the last topic of this presentation, let's talk about routing. Now, routing can be notoriously difficult, but it really doesn't have to be. Think of it this way. Our model is still our single source of truth. So our model determines where we are in our application. We make changes to the model with updates which are triggered by actions. So we can make everything to do with navigation through an application work with actions and our model. Then we can add routing on top of that, and it's just a simple mapping from routes to actions. Everything else works the same. Let's look at a simple routing example. Here I have 3 different pages in the application, and on the left I have tabs or links that use routes to navigate, and on the right I have buttons that trigger actions. And the point here is that we want to make sure that using links with routes or actions have the same result. We can implement this with pages which are just constants for our pages with unique IDs and tabs to say in which tab those pages live. IDs are unique, but you can have more than one page in the same tab. For example, here, the beer and the beer details page are in the beer tab. Now to navigate, we will set those page constants on the model to say where we are in the application. So when we navigate to a page, it's just a matter of putting those constants and any parameters and assign them to the model. When we navigate to a page, we can also say that we need to first load some data from the server. So for example, here we have navigate to beer, which will load the beer from the server first, update the beer list on the model, and then navigate to the page. From this create navigation function, we're returning functions that are easy and convenient to call to navigate to a page. And the callers do not need to know the details of what's going on in order to get to the page. Our app will create our components and will create ourselves a lookup map from page ID to component so that it's easy to figure out from the model which component to render. So in the view function, we look at the page ID from the model, we find our corresponding component, and then we just have to call view on it to render it. We can also look at the tab in the model to determine which is the active tab and highlight it appropriately. So at that point, everything works with actions. Adding routes is just a simple mapping. Here we are mapping routes to objects with the ID of the page that it corresponds to and the action to call to get there. Because it's so simple, you can use just about any routing library that you want. Here I'm purposely using a very simple library called URL Mapper. We take the route from the document location and then we call URL mapper.map. We pass in the route and our definition of routes, which was just a mapping between routes and objects. We find the corresponding result, and whatever gets resolved is whatever we put, which was an object with an ID and an action. So we could just call the action and pass in the values to navigate to that page. Finally, we associate our resolve route function to window.onPopState, and that will ensure that a function gets called every time the URL changes. Now that works, but the only problem is that if we navigate to a page with an action, the URL in the browser's location bar will not match. It's easy to fix though. We can easily create a reverse lookup. So we'll take all our IDs of our pages and we'll map those to the corresponding route. Then, every time the model changes, we can look at the model page ID, find the corresponding route segment, and then use URL mapper stringify to turn that into a final route by passing in the parameters. Then we look at the document location hash, and if it doesn't match what the route's supposed to be, we can just set it with window.history.pushState. With that in hand, we can see that now if we navigate to a page even with an action, the URL in the browser's location bar matches. It even works with the tracer. If you go back and scroll through different models, you will see that the location bar in the browser matches the place that we are on the page. And it works even when you type in directly the text area. And the point of that is that, again, our model is our single source of truth, and everything else bases on that to render the view. So as you have seen, meiosis is just a pattern, and a lot of your code is just plain objects and functions. Nothing is tied to any specific library. So when you open a file, you don't have an import of meiosis or anything else to manage your application state. This makes your code a lot easier to write, maintain, and reuse. I hope you enjoyed this presentation, and you will find more documentation, all the examples on the Meiosis website. Have a look, try out the tracer, and join us on the Gitter chat. Thank you very much and enjoy.